Welcome.
Thank you. So, is C++ a safe language? Well, I would say compare with what? I mean, is it safer than C? Sometimes. Depends how you use it. Oh, I forgot something relevant. It doesn't work. Okay. So, who am I? Well, I am a C++ programmer. I started programming, writing code in C++ in 1989. So I got my first internship, and my boss told me, okay, you are going to write a prototype in a new programming language. I think you will never use it again. This is not going to do the job, but try to write the prototype. That was many years ago, and I still write C++ code. In my spare time, I am a professor in computer architecture at my university, one of the many universities in Madrid. And I say in my spare time because my main job is I am a C++ programmer. And I am also a member of the C++ committee. I am the so-called head of delegation of the Spanish delegation in the C++ committee. Okay, I am the Spanish C++ delegation because nobody else wants to go. And my goal for a long time has been try to improve applications programming. And this has multiple dimensions, better performance, better energy efficiency, but also making code more maintainable and more reliable. So I think today we will focus mostly in the reliable or safety part. So let's start with the safety problem. So perhaps you have heard of this. It was published last year by the Open Source Security Foundation and the Linux Foundation. And in this security mobilization plan, they identified that one of the routes for the future was to eliminate root causes of many vulnerabilities through replacement on non-memory safe languages like C and C++. This is what they said. Each time I have read one of these reports, they refer a lot to kernel code. Do you know much kernel code written in C++? Much? Well, yours. That is yours. Yeah. Anything else? Okay, then November 2022, the NSA delivers another report, commonly used language, and when they say a list of languages is just C and C++, provide a lot of freedom and flexibility. They take you to simple mistakes that can lead to exploitable memory-based vulnerabilities. So they encourage people not to use languages as C and C++, short list, and then give a long list of alternatives. And then January this year, we got this other report from Consumer Reports about the feature of memory safety. And it was again the same story. So each time I see this C/C++ language, my first reaction is, sorry, that language does not exist. Either it is C or it is C++. I don't know the C/C++ language. Okay, so reading all this, something came to my mind. Well, first, this is the IOBI index, and we can argue a lot if this is a good index or not. They try to measure popularity. So this horrible language that nobody should be using is growing and growing and growing. And if you add this to C, is a huge portion of the market. Also, they named the programming language of the year for 2022 C++. So as I said, I was thinking about all this, and then this guy came to my mind, Fred Brooks. You've probably heard about the book, The Mythical Man Month, but this is not what I was thinking about. I was thinking about this paper he published in 1987, No Silver Bullet, Essence and Accidents of Software Engineering. Well, curiously, he published this book the year I started my studies at university, 1987. Okay, and why this came to my mind? Because one thing he says in this paper is that there are, in software, two kinds of complexity. There is essential complexity, which is inherent to your problem domain, and there is accidental complexity, which is something that you could eventually remove from your system. And how do we remove accidental complexity? Well, Brooks says that the best approach is growing software organically through incremental development. And we have tried the other way around, which is let's replace this by a different language many times. I mean, since I started programming, every few years, I've seen the new programming language that is going to kill C++. Okay, last year was special because we had 3 programming languages that were going to kill C++. Well, we are still waiting. So because this way of replacing didn't work very well, perhaps we should follow Brooks' advice and try to evolve incrementally to a better solution. So, memory safety, is it accidental or essential? I would say, and we can argue for hours about this, but I would say that memory safety is something accidental that can be fixed. But we could argue about this. And why should I consider that a programming language is different from any other software product? And I cannot take the same route of incrementally improving it. So if you are interested in the other way around, you can go to a different talk of one of the many languages that came to save the world. I'm not here to save the world. Just let's try to at least to improve the situation a little bit. So, safety. Well, the first problem with safety is that safety has many meanings, or it has many dimensions. We could think about logical safety, so those mistakes that I make because I do not express properly the logic of my program. Resource safety, which canonical example is probably memory leaks. We know more or less how to cope with this. We have concurrency safety and data races, did logs and all this stuff. We have memory safety, but we also have type safety. So do we really respect the type system or not? conversion safety, timing safety, achieving the deadlines, and termination safety. So all these are different kinds of safety that I need to consider. If I focus in memory safety, I could have some general guiding principles, like make sure that a pointer points either to null PTR, to the null pointer, or to a valid object. That any access through a pointer never refers to null pointer, and an access through a subscript is always within the bounds of the range of the array. Now, safety dimensions are not independent. No, they are not completely independent, because for getting memory safety, I need also to ensure that an object is accessed with the type it was defined, which means that for memory safety, I need type safety. And an object, I need to guarantee that an object is properly constructed and destroyed. And this is resource safety. So all these safety dimensions are not fully orthogonal. For achieving some of them, I need to some extent to achieve the other dimensions. So if I try to solve the problem or to achieve some improvement, I would not claim solving the problem. In C++, I need to consider some constraints. First one is that C++ is used in many different domains. And that means that in different domains, we will find different sets of priorities. One of them is the trade-off between performance and safety. So if you ask in some domains, they will tell you, give me safety as long as you don't make my program slower. While in a different domain might be, hey, I can live with a slower program as long as it is safe. Radical changes in C++ is not acceptable, are not acceptable. Each time that you propose something, the first thing that users will tell you is, please don't break my code. So the code that exists today should go on compiling after the changes we make. And this is a very difficult constraint for solving the problem. Well, sometimes we break from one version to another version a little bit, but always thinking that there is a reasonable migration path. And as I said before, new languages are tried out constantly, and they usually fail. So the other way of doing things is taking the evolutionary approach. So in the last months, Bjarne Stroustrup has been advocating a different solution that I agree on, and is defining profiles to the language. So we have C++, but we may have one or more profiles that you optionally enable in the language. And this profile will add a set of additional constraints. So even if I lived for 1 year in Germany, my German is not so good, sorry. Okay, so a profile would combine several things. One would be a set of additional coding rules. So we will not accept if you enable the profile everything that is valid in C++. That is the price that you have to pay to get additional safety. Now, the rules cannot be seen isolated. The rules are coherent sets that will help you to achieve more safety. The final goal is to simplify the code. But this is not enough. We also need support libraries. We need libraries that allows you to do safely things that we have removed because of the rules. And the third component is static analysis tools that will allow us to identify those cases where the code is not safe or not safe enough. So I will give you some examples. This is not in a talk. We do not cover everything. And also because this is an ongoing work right now. But there are some things that we can do today. So let's start with initialization. A guiding principle should be that every object is accessed with the type it was originally defined. Because as soon as we bypass the type system, we will definitely find ways of having a memory safety problem. And this has some consequences, like a rule for always initializing every object, avoid any kind of unsafe casts, because it's another way of just bypassing the type system. Avoid unsafe unions, because today we have variants. So for most cases of what you need in application code and you are using a union, a variant will work quite well. And we will need also a number of rules to avoid unsafe use of pointers. So this is a very simple example that any tool and even a compiler can detect that I have here something that has not been initialized. Okay? So I would get by my tooling an identification that this variable needs to be initialized, because otherwise there is some path in which the variable has not been initialized and I am returning the value. Or I could even do better and initialize with a lambda that is immediately invoked. Now, from time to time, there are cases where I need that something is not initialized. A typical case of this is a buffer, a large buffer of bytes that I have locally and that probably I am going to read from a communication port or from a file. I don't want to initialize something and then just overwrite. So for these cases, what we could do in the language is to add an annotation where we say, this is initialized, but this is intentional. If we don't have, or while we don't have the attribute, we could add some annotation depending on our static analysis tool to just locally allow that a variable is not initialized. But this should be a very rare case. There are very rare cases where this is really needed. Now, other problem partially related to initialization and to pointers is dangling pointers and dangling references. My guiding principle here is that every pointer points either to a valid object or to the null pointer. This is what I want to guarantee. If I guarantee this, I will be much nearer from memory safety. So My first problem is defining what's a pointer. I mean, a pointer might be a row pointer, but there are many other things that are a pointer. A reference, a container of pointers, a smart pointer, a lambda capture of a pointer. So all these things are also conceptually a pointer. They point somewhere else. So dangling pointers in general seem a hard thing to detect. For example, I could look at this good-looking function that take a pointer to an element, do something with the pointer, and delete the pointer. And if I look locally at that function, I say, okay, why not? And then I have this other function that is also good looking, where I allocate an element, I call f with the pointer, and then I do some more things. Well, if you look then separately, because they are in different translation units, and probably you cannot analyze them at the same time in a large application, then you could conclude that each of them individually seem okay. But if you look together, you see here there is a bad thing happening. At least you have a dangling reference, and then if you want more, you have a double fake. Okay, we know this because I put these two functions here. Now, if I give you these two functions in 2 million lines of code, it's not so easy. So I'll come back to this example later. So we need to eliminate those cases where we get dangling pointers or dangling references, because otherwise we have no type safety, we have no memory safety, and we have no resource safety. Scary. So the rules we introduce, and some of these you may find already in the CPP core guidelines, are based on differentiating two kinds of pointers. Those pointers that are owners, that is, they are responsible of a resource, and those pointers that are non-owners. So any smart pointer is an owner. Your unique pointer is an owner. Your shared pointer, it's an owner. But then we also add one more type. In this case, I am using the one that is in the GSL, the Guideline Support Library. There is a version of this library available on GitHub. And the GSL owner T star is also an owner. By the way, you will see very soon that this is a type def for a T star. So it's not a class, it's something very, very simple, but it allows you to mark in the code your intention when this is a pointer that is handling a resource and when it is not. And by default, we say that all row pointers are non-owners. So all row pointers do not manage memory. This is a simple rule. I could eventually think of a not owner, but I don't need. I say all row pointers have nothing to do with memory management. And now I can identify which pointers are escaping outside their scope. Escaping from a scope can be done in many ways, returning, but also throwing the pointer, or having an out parameter, or a capture, or so on. Okay, we have all these ways of escaping. So what we have to decide is when escaping is okay and when escaping is not okay. And the rule is simple. A pointer can be returned, can escape from a scope if it was passed to that scope. So the scope is not the owner. I gave you something, you can return me something as an argument, or it was written from an external object that has a larger scope, or it points to an object external to the scope. It was obtained by new, okay, it can escape, or in general, it outlives the scope. Otherwise, the pointer cannot be returned, cannot escape. And this is something that I can analyze locally without taking into consideration what is happening in any other function. Of course, this imposes strong limitations of what you can do and you cannot do in a function. And you could tell me, okay, you are forbidding me this corner case, that should be okay. And we'll say, yes. Bad luck. But with this rule, I can guarantee that you are not getting the dangling reference problem. Okay? So let's go to resource safety, and then we will put this thing together. So we have a number of ownership abstractions, and by default, what we should try is to use these ownership abstractions. That are all those abstractions based in the AII pattern, the best idea with the worst name in C++. Resource acquisition is initialization. So you acquire the resource in the constructor or later. This one, almost I got it. Okay. And then you release the resource in the destructor or before. And if you follow this and you add move semantics, this abstraction is resource safe. We have many of these ownership abstractions in the standard library. You have vector, you have map, you have string, you have unique pointer, you have fstream, you have jthread. All these abstractions are safe. For low-level things, when none of those things fits, usually because you are implementing one of those things, then you have GSL owner. And this is all the definition of GSL owner. For any type T, owner is T. That's enough. So GSL owner of T star is essentially a type def for T star. But it simplifies my code because now I make explicit those cases where it is an owning abstraction. It makes easier code reviews and has no impact on ABI, which is also important. So owner is good for implementing your own ownership abstractions and avoiding ABI breaks. Owner is bad for wide use in your application. Please do not use everywhere owner. Use owner just to implement your abstraction and encapsulate it. And if you have too many owners, it means that you are having C-like interfaces. And C-like interfaces are usually not really safe. My ownership rules. A pointer returned by new is an owner. So if you have a new, be sure that you assign the new to an owner. Only owner pointers can be deleted. So any row pointer you cannot delete. You can only delete if it is an owner. An owner passed to a scope must be deleted or passed to another scope as an owner. And a pointer passed to a scope as an owner is invalidated And once a pointer has been invalidated, you cannot use any longer. So let me put this in an example by taking our previous example. You remember this example where I could not easily reason, and let's migrate to use owner. So in function f, I am going to take a GSL owner element start. Okay, and now because I take an owner and the owner is not escaping of this function, I can locally analyze that this delete is okay. Because I got an owner, I'm not giving the owner to nobody else, I must delete. If I don't delete this pointer, I will get by my tooling an identification that you are leaking a resource. Now, if you look to the other side, to the color side, I have an owner which has been initialized to new, and then I call f with this pointer. This is okay. Now, my analyzer locally will also identify, hey, you have passed an owner to another function, and you are trying to use that pointer later. Don't do that, because you are using an invalidated owner. You cannot do that. And you cannot delete an invalidated owner either. So now I can analyze each part separately. And that was the idea, because global analysis of large applications might be too time consuming, but local analysis, translation unit per translation unit, is something acceptable. I can use owners also to implement abstraction. So if I wanted to implement a vector class, I have as an owner the pointer that holds something that needs to be deleted. But these other are row pointers because they are pointing to different places in the buffer. So, okay, they are row pointers. So I said at the beginning, we want also sometimes to extend the library with types that might add additional checks. And we have two cases. One is detecting null pointer errors, and another is bounce checking. So for null pointers, we have the rule, a pointer may point to a valid object or to a null pointer. So in regular code, I could write these two functions. This is checking that the pointer is not null. This is not checking. And then when I write client code, sometimes I have to know, okay, if I pass a pointer, first I have to check against null, and in other cases not. And I cannot detect which checks I should do, which checks I should not do, because compilers do not read manuals or documentation. So what I can do is use GSL not null, and a not null type is, this is a type, is not a type def, that on construction will check that the pointer is not null. And then you can safely use this pointer. So now if you have a function that will only work with a non-null pointer, you just take a not null element star and you are done. Now the checker can tell you, hey, this check is redundant, remove it, because it is already a not null. And this is okay, you can perform this call safely because this is a non-null pointer. And on the other side, I can also detect which checks are redundant, because if I am checking to call a function that takes a not null, I don't need to perform that check. So again, I can find those checks. And for accessing ranges, if I write something like this, this is unsafe. I should use pointers only for single objects. For spans, I can use GSL span. Okay, and this is always range checked. And this is a difference between GSL span and STD span. Unfortunately, STD span never performs range checking. So for safety critical code, I would never use std span. Use instead GSL span or your own span class that performs range checking. And if I want to traverse an array like this, okay, this version uses a primitive array. This is fast, but it is unsafe. On the other hand, I could use an std span, a GSL span. With the GSL span, this is safe, but it has additional checking. So what I can do is just use a span, but with a range for loop, and now I have both. I have it safe and fast because I don't need to make range checking. And for low-level code, well, in all systems, you have code that is really low level and that needs to do the dirty things. Other programming languages solve the problem by giving that part to C++, but